Alright guys, so here's what you should have seen in all of this activity, the exploring electricity activity that we did before. So I'm going to go over kind of the stuff that you should see as the key so we can make sure to have all be on the same page for when we come back, because we're probably going to have a quiz when we come back, but whatever, we don't have to worry about that now. So to begin, we explored and we kind of said, okay, what happens when you rub a balloon against your head? Obviously, it makes your hair stand up. You've probably seen that before. And what can the balloon do after you rubbed it against your hair? Things can stick to it. It sticks to the wall, right? It causes some kind of force of attraction, which is weird because how does it do that? How does it cause a force of attraction? So what is causing this force of attraction? It might be magnetism, right? Because it's not gravity and there's no really any other forces. It's probably magnetism in some way. So magnetic attraction is caused by some kinds of charges, so we need some kinds of charges in there. So we went to this simulation first, and we showed, we played with Sims and chemistry and the balloon thing. So when you rub the balloon on the sweater, what happens? The first thing that happens is the electrons rub off the sweater and onto the balloon. Off the sweater, onto the balloon. And that causes then, electrons rub off the sweater and on the balloon, and that causes the balloon to be attracted to the sweater, right? Causes the balloon to be attracted to the sweater because there's a difference in charges now. We've got the positive charges on the sweater and the negative charges on the balloon. So why does the balloon we did that already. And bring the balloon close to the wall, and what do you observe? So let's rub all the electrons off the sweater, like that. We bring it close to the wall, and we actually see that the wall's electrons do something. Custodial's in. That's what you hear in the background. That's okay. So we see that the electrons in the wall we're doing something because of the electrons in the balloon. And what are the electrons in the wall doing? They are moving away from the electrons in the balloon. They are repelling from the electrons in the balloon. And why are they repelling? Because they are also negative. They're also negative, right? So the balloon sticks to the wall. It's not really attracted to the wall, but it does stick to the wall because we've kind of induced a magnetic field in the wall by pushing some of those electrons away. So right where the wall and the balloon meet, those protons are a little bit more exposed, and so the negative balloon kind of sticks to the wall. Negative balloon kind of sticks to the wall there. Okay, so that is this first page where we have the electrons in the wall are repelled, and the electrons in the wall want to move away from the excess electrons in the balloon. Okay. So, going on to the second part of this. So the phenomenon we're witnessing right here is called static electricity. And we've seen this before. Things come out of the dryer. If you didn't use a dryer sheet, right, things are very staticky. The socks stick to each other and stick to you. They stick to whatever. And also the like little bits of paper or whatnot stick to your socks and stick to your clothes. So you can use a dryer sheet or some kind of anti-static thing to stop this from happening, because these things all stick together because of magnetism. Magnetism, positive and negative things attract each other. Now in here, you may have gone over to the two balloon thing. If you reset the balloons, not only can things attract to each other, so we'll rub about half the electrons off on this balloon and then about half onto this balloon, you can also get things that repel each other. So these two balloons, because they both have negative charges, do not want to be next to each other. They repel each other. Let's get this wall out of the way. So you can actually make this balloon repel off this other balloon. It does not want to be. It wants to be on the sweater because the sweater is positive and the balloon is negative, but these two balloons are repelling each other because they don't want to be next to each other because they both have an excess of negative. Both have an excess of negatives, so the balloons are repelling each other. Okay, so that is that first part. So the phenomenon we talked about is static electricity. From the Wikipedia page on static electricity, what is the definition? So we've looked on there, and we see the definition of static electricity is an imbalance of electric charges within or on the surface of a material. And the other type of electricity that is not static electricity, that is normally running through wires and whatnot, is called current electricity. And it's different from static electricity in that electrons move in current electricity. We see with the balloons on here that it does not, these do not move, right? These electrons are being rubbed off, but they do not move in static electricity. But current electricity, they do. So in order to get static electricity, we have the same thing that is on here. You have to scrape to scrape them off, physically rub something against something else in order to get something static electrically charged. There we go. So that was D. What has to happen? Electrons from one thing must be scraped off by another thing. We can't get that without actually scraping things off. And then, what is static discharge? Static discharge occurs when the electrons flow out of one material due to the imbalance of electrons. All these electrons in here, all being negative, they want to get away from each other, but they can't because they're stuck on the surface of the balloon. So they want to all get away from each other. So if they could flow out of the balloon, they would, but they cannot because they can't move on the surface of the balloon. But some things, some insulators where the electrons cannot move, can move the electrons a little tiny bit. So this is evident like when you have lightning. So when you have lightning strike, that is the excess of electrons in the cloud jumping down to the ground. That's static discharge. And when you shock yourself, static shock, right, you have, you rub your feet on the ground, which we can illustrate in the next one, the next simulation. So go ahead and go on to the next one, the John Travoltage simulation, which is this one. And he rubs his foot on the ground and picks up a bunch of electrons. And this is static electricity, right? The electrons are not really moving through the material. They're kind of moving a little bit, so it's maybe not completely static, but they do kind of move throughout him. And because the electrons are mostly negative, they do want to get away from each other, right? You see these electrons spreading throughout. The electrons repel each other, so they kind of want to spread throughout. Now, they have nowhere to go right now, so it's not until we bring his hand close enough to the door, close enough to the door to have them run out. Now, depending on how many electrons there are, they might jump through the air quite a lot. Sometimes, if there's only a few electrons, they have to get really close before they can jump through. But if there's a lot of electrons in there, they don't even have to get very close at all. They can run straight out. Now, let's show that if it's really close, just a few electrons on there can run out. Just a few electrons on there can run through. So how far the electrons have to go through the air really determines what buildup there needs to be, right? That's why lightning, that has to go through a huge amount of air, all the way from the sky down to the ground, that is a huge amount of electrons. A giant voltage has to build up before lightning will exist. If the clouds were really close to the ground, then you might see a little tiny, tiny ones, or if the clouds were in contact with the ground, you might not see it at all. So if you have his finger far away, his hand far away, from that we need a large number of electrons before it will actually flow out, right? Large number of electrons before it will actually flow out. There they go. And once that connection is established, then you can get it flowing a little bit easier. But anyway, so describe what happens in this PHET simulation. So John Travolta's foot scrapes along the rug, scrapes the electrons off, which spread throughout his body. When his hand gets close to the metal, the electrons flow out as an electric spark, as you saw. So where they come from and where are they going? They are coming from the rug. So they come from the rug and they go to the metal. The reason why they go through the metal is because metals are conductive, right? That is like an electron sink over there. Okay, so the next question on there, how are these electrons behaving differently in the simulation from the last one? In this one, the electrons can move around a little, right? We scrape them off the rug and they're moving around a little bit, not a lot, but it's different from this one because they could not move at all. So in this one, we reset the balloons, they move from one thing to another, but once they're on this balloon, they don't move at all. There's no discharge from the balloon. Okay, not that one, this one. Okay, so move around a little. So is this true static electricity? Some people would say yes, some people would say no. Some people would say, no, this is currents because the electrons are moving, but other people would say, nah, this is still static because the electrons cannot move that much. There's nothing for them to go to. It's still a buildup of electrons, so it still fits the definition of static electricity. Okay, so that is 6C. So now on to 7. What types of materials conduct very well? Obviously, metals conduct very well. Copper, silver, gold, platinum, aluminum. And number 8, why is this? So remembering back to metallic bonding, why is this that that electrons go through metals very well, and it's really because of the bonding type. Electrons are, remember that word, delocalized in metallic bonding. So in metallic bonding, the electrons are delocalized. And what does that mean? It means that this is what the electrons look like. In our zinc, we'll make this a little bit bigger so you can see it better. In our zinc, the electrons are able to move around, right? The electrons inside here are delocalized. They're able to move around. Remember, nobody wants them. All the zincs want to lose electrons, and so the electrons are pushed off all the zincs, and so the electrons can simply move throughout the entire zinc. The electrons are able to move. Now, number 10 says ionic compounds do not conduct electricity in their solid form, and so if you Google what ionic compounds look like, you'll get an NaCl crystal. And this is essentially what they look like. You have this very ordered pattern of sodium and chloride ions this time. Sodium and chloride ions. They're not individual elements. They are now, or not individual particles like we had in the zinc. Now they are ions, positives and negatives. And you guys probably just drew them as circles that were bigger and smaller, and that's fine. The smaller circles were sodiums and the larger circles were chlorines in this case, because as you go across the periodic table, the radius increases, and sodium and chlorine are actually in the same row of the periodic table, so sodium must be smaller than chlorine. Okay, so how is this different from the metal? How is this different from this? In this, there are none of those free electrons. Those electrons are all locked in place in this NaCl crystal. There are no free electrons, there's only ions. No free electrons in the ionic compound, there's just ions in there. Okay, and what can the electrons do in the metal structure that they cannot do in the crystal lattice? Here they can move around. The electrons are free to move around throughout the material. They can move from one side to the other. So, hopefully we're starting to get an idea as to what electricity is, what static and current electricity is. Electricity, just as we see on here, is nothing more than moving electrons. Electrons as they flow from one thing to another. And this is kind of, right? So electricity flows from one thing to another. The difference between this and normal electricity through a wire is that this has a large resistance to that flow and wires generally don't. So electricity is nothing more than moving electrons. Electrons that move from one place to another. And they move really easily through metals. Going on to the next summary bit. Why can metals conduct electricity? Use diagrams to explain. So, oops, shaky. Metals conduct electricity because the electrons are free to move. So through the zinc itself, right, through the particle, through the wire of zinc, or the mass of the zinc, the electrons can simply move straight through. So that's why metals are conductive, because the metals can delocalize their electrons and they move straight through. So why can ionic compounds not do this? Because there's no free electrons. There's nowhere for them to move. They're going to be repelled by this ion. They may be attracted to this ion, but they can only go so far. The electrons cannot move through an ionically bonded substance. All right, so next we will explore what types of materials can conduct electricity when dissolved in water. Can water conduct electricity by itself? Most people would say yes, because that's what they are used to seeing, right? If you drop a toaster into a bathtub, while you're sitting in the bathtub, you will in fact die because you will get electrocuted. But as we see on the next simulation, the sugar and salt simulation, so you went here, and then you clicked on the simulation, so that simulation is here. And focus on there we go. So we take we should start here on the macro side. So we take our conductivity tester, we stick it down inside the water, and we, oh wait, reset. I think I had some in there. There we go. Conductivity tester, and the light bulb does not light up just with a regular water. So with regular water, light bulb does not light up, which means water is not conductive by itself. Generally, water that you just see out randomly, like in your bathtub or in puddles or in lakes or the ocean, that water has stuff dissolved in it. It is not pure water. The water even that comes out of the faucet at home has small amounts of stuff dissolved in it. It's not the water itself, but it's the dissolved stuff that causes the water to conduct. So on here, right, what other materials can conduct electricity? Can water conduct electricity by itself? Nope, it cannot conduct electricity, even though probably most people think it can. So putting that conductivity thing into the water, did the water conduct electricity by itself? It did not. Water is not conductive by itself. Okay, so next, let's put some stuff in there and see what happens. So B on there says, shake some salt into the water and make your observations, just a little bit. And we see the light bulb starts to light up with the salt. And then the next one, continue shaking the salt into water, describe your observations. The light gets brighter. The more salt we put in. The more salt we put in, the brighter the light gets. More salt means brighter light. So as the concentration of salt increases, the conductivity of the water increases. So there must be something in the salt that is causing this to be conductive, right? Must be causing that to be conductive. Now, if we move this down, right, we have no more salt in our shaker up here, but if we move this down into the water and we cause some evaporation to occur, let's look at what happens. So we cause some evaporation to occur, and the light gets even brighter, and the salt concentration increases. That is interesting. So light gets brighter and brighter and brighter until it cannot get any brighter at all. And then we have a large concentration of salt. That's odd. Now let's add some water to this and see what happens. Very quickly the light gets dimmer and the concentration of salt decreases. So we add pure water to this and the concentration goes down and the short circuit evaporates. There we go. It's because we had water on both sides of the battery, and so the battery was just going straight around and depleting itself. If you did that to an actual battery, it would very quickly deplete itself, and it would, but that doesn't matter. All right, so when we evaporate water, it looks like the concentration of that salt increases. And when we add more pure water, the concentration of that salt decreases, and that's directly linked to the conductivity of that water. So that's interesting. Okay, anyway, so then it says to click reset all. So now we're on 16D. So 16D, click reset all, and go to the sugar. So click over here on the sugar, and then we pour some of that sugar inside into, we forgot to put the conductivity tester in there. So reset all, put the conductivity tester in there, put some sugar in there. All right, so record the observations with sugar inside there. So we see with sugar, the light bulb does not light up. And it doesn't matter how much sugar we put in, lots and lots of sugar inside there, sugary water, the light bulb does not light up. So something must be different with sugar that makes it not able to conduct electricity. Something must be different with the sugar. All right, going on to the next page, right, we'll head on here, so still no light, right, lots of sugar in there, still no light. So let's try to figure out why this is. What about salt, when it's dissolved, conducts electricity? Because remember, salt, when it was as a solid, did not conduct electricity because it was our crystal lattice. And the crystal lattice could not conduct electricity because you could not get electrons to go through. So in a solid form, salt did not conduct electricity. But in our solution, when it's dissolved in water, salt definitely does conduct electricity. Put salt in there. So as a solid, it did not conduct electricity, whereas as a solution, it did conduct electricity. So let's see if we can figure out why that is. So we go to the micro, and that just means we can see the particles now. And we take note of the two solutes. So here's the two solutes, sodium chloride and sucrose. That is the actual chemical name of salt and the chemical name for sugar. And so we take note of the two solutes. Salt is sodium chloride, sugar is sucrose. Based on the formula, what type of bonding would NaCl have? So sodium, hopefully you remember, is a metal because it's to the left of the stair step, and chlorine is a non-metal because it's to the right of the stair step. And when you put a metal and a non-metal together, you get ionic. You get ionic bonding. So metal and non-metal means ionic bonding. So this would have ionic. Then B, based on the formula, what type of bonding should C12H32O11 have? This, carbon is a non-metal, oxygen is a non-metal. Remember, hydrogen you kind of leave out because it's weird. So you have a metal, you have a non-metal and non-metal, so it's all non-metals. And when you have all non-metals, you have covalent. You have covalent. So you have non-metals, you have covalent. You have metal and non-metal, you have ionic. So would you expect this compound to be soluble with water? And remember, the things that are soluble with water are the things that mostly contain oxygen, because oxygen makes the compound polar. Remember how that makes it polar? Because all carbon to oxygen bonds are polar and all oxygen to hydrogen bonds are polar, so no matter what it's connected to in there, you're going to get some polar bonds. Okay, so shake some sodium chloride into water and record your observations. So now we can see the actual particles. When we shake the particles in there, what do we see? They no longer are sodiums, which are the pink ones. We see the pink ones are sodiums, and chlorines together. They are separate. So the particles break apart and form Na plus and Cl minus, and then they move randomly throughout the water. So that is an important thing to note. For 17D, the particles break apart and form Na plus and Cl minus particles, or ions, within the water. They move randomly throughout the water. So the particles are moving randomly throughout that water inside there. Okay, now we reset the whole thing. Reset. And we put some sucrose inside there. So we add sucrose, and let's see how that's different. So we shake some sucrose in there. There's our sucrose molecules, or sucrose crystals. And how does that look different? Now, granted, these particles are individually, ones are smaller than the other ones, but that's just because sucrose is way, way bigger than sodium chloride. So you'll be able to see it. The molecules have to be kind of smaller. So here we have sucrose molecules. How is that different from the Na and the Cl? Let's put some NaCl in there as well and see how it's different. The NaCl broke apart into individual charged things called ions. Those individual charged things are called ions. And so the sucrose did not break apart into ions. Instead, it stayed as covalently bonded molecules. So that is different. That's how sugar and salt are different in the water. And remember, salt is the stuff that conducts electricity, whereas sucrose does not conduct electricity. So let's go over that, what we should have seen on here. So the sucrose molecules break into large clumps and stay as clumps. They're staying as molecules. And NaCl formed ions in the waters, whereas sucrose stayed as molecules. This is the main difference between an ionic compound and a covalently bonded compound, also called a molecular compound. Ionic compounds, when they dissolve, they break apart into their ions, into Na plus and Cl minus in this case. The sucrose, molecularly bonded compounds, covalently bonded compounds, all the same thing, these stay as molecules. They do not break apart into ions. Okay, so the summary question right underneath: in order for a compound to conduct electricity when dissolved, it must break apart into charged particles. Use this idea to make a general statement about what types of compounds will conduct electricity when dissolved in water. So soluble ionic compounds will conduct electricity in water. Covalent compounds will not. So things that have ionic compounds in water will conduct, and covalent ones will not conduct in water. So only soluble, meaning they dissolve. Not all ionic compounds will dissolve. For example, brick is made of somewhat of calcium carbonate, and calcium carbonate does not dissolve in water. You can put a brick out on the street and it will not dissolve. Right? Calcium carbonate's insoluble. So it has to not only dissolve, but it has to break apart into ions, be ionic when it dissolves. Okay, so next, click on the water tab on the top. So water tab up here, and we see what's happening. So let's reset those. Reset. So what are these particles doing all the time? As particles of a liquid are doing, right? They are moving all the time, and they're bumping into each other, and they have the freedom to move around. This is probably pretty cold water because they're not very far apart, and they don't move around a lot, but they're still moving around, right? They can move past each other. They're not locked in place. You see, if you track one water molecule, it is moving through, right? It's not always connected to the same ones, although this one's not moving that much. Let's look at one of the ones over here, maybe. It's not always connected or always by the same water molecules, right? It moves around throughout. Right? It's over here now. So definitely not a solid, just vibrating in place, and definitely not a gas where they're all moving freely and randomly in all directions, and there's large spaces between where they move, but in a liquid, that it is still heavily attracted to each other, but can move around a lot. Okay, and then on to, so that's 19A, 19B, drag the salt crystal into the water, particles, and record your observation. So here's the salt. We drag this inside here, and immediately it breaks apart, right? The water molecules very quickly break apart the sodiums and the chlorides, and they do this by colliding. They physically collide with them and break them apart. The waters immediately separate them into their ions. You see the small sodium ions and the large chloride ions, because as you go across the periodic table from left to right, the radius increases. All right, let's see how that's different from, see which parts of the water molecules are attracted to the Na and which parts are attracted to the Cl. It's a little bit hard to see, but you can kind of see what's close to the Na, right? More of the red ones are close to the Na, and as they, not always, but more of the red parts are going to be close to the Na, and more of the white parts, you can kind of see, are close to the Cl. You see how more of the white things. So the red things are the oxygen, and the white things, get it back on there. The white things are the hydrogens. Why would the oxygen be attracted to the Na and the white things, the hydrogens, be attracted to the Cl? Because, as we know, water is polar. Right, we have these partial negatives and partial positives inside there. The electrons are pulled toward the oxygen because the oxygen is more electronegative than the hydrogen, and so the electrons pull toward the oxygen, making the oxygen slightly negative. And that slightly negative thing is attracted to the positives of the sodium. And the slightly positive thing is attracted to the negatives of the chloride ion. So they form what are called these hydration spheres around the sodiums and form this very ordered way of arranging themselves around the sodiums. Not to mean they can't move, right? They're not locked in place either, but they're generally more of the negatives are near the positive and more of the positives are near the negatives. All right, reset. So looking on here as to why that is, right? Oxygens are attracted to the sodium and the chlorides are attracted to the hydrogens because water is polar. We've seen that before. Oxygen slightly negative and hydrogen slightly positive. And we click the partial pressures box, partial charges. The partial positives are attracted to the negative ion and the partial negatives are attracted to the positive ion, the fundamental rules of Coulomb's law that opposite charges attract. All right, so we hit reset all and we look at what happens to the sugars inside there. What happens to the sugar? So here's the sugar. Here's the sugars, and this is actual size now, so much actually bigger than the salt ones. So there's 2 sugars. This is one sugar molecule and 2 sugar molecules, and they're connected by also the positives and negatives that are inside there. The partial positives and partial negatives because they're not ions. So we see the same thing happen when we let this go. Very quickly, water separates them, and that's what has to happen in order to dissolve. The waters have to separate the individual parts of it. But you see something that does not happen. The carbons, hydrogens, and oxygens do not separate from each other. They stay as a molecule inside here. They stay as a molecule, even though they are being buffeted around by the waters, they stay covalent. So covalent bonds do not break when you put them into water. Ionic bonds do break when you put them into water. There goes. So sodium and chloride, the ionic bonds break when you put them into water, float around as ions. Covalent bonds do not break, right? They break apart into molecules, but the covalent bonds of the molecule do not break when you put them into water. So the next question, why are the water molecules attracted to the sugar molecules at all? Well, the only thing that causes attraction is partial positives and negatives, right? The sugar molecules must be polar in some way. Otherwise, there would be no attraction between the water molecules and the sugar molecules. And we'd be pretty sure they are polar because the oxygens, there's so many oxygens in the sugar molecule and so many polar bonds in the sugar molecule, so they must be polar, right? We're not going to draw them out. You drew sugar molecules enough in biology, we don't have to do it at this time. Okay, so that is those sugar molecules, right? As we see on here, sugar molecules must be polar in order for them to dissolve in water, and that must be true of all covalent compounds. Covalently bonded compounds must be polar in order to dissolve in water. Okay, so here's what we should have learned today in very simple fill-in-the-blank activity. So, things we need to have learned by this end of this activity, and make sure we know these for when we come back. Electricity is caused by moving electrons. Metals can conduct electricity because in metallic bonding, electrons are delocalized, so they can move around freely. Ionic compounds cannot conduct electricity because their electrons are locked in place. They cannot move, or you can say they're localized. So electricity is just moving electrons. Electrons can move through metals because their electrons are already delocalized. Ionic compounds, they cannot, because they are not delocalized. They are locked in place. Number 4, in an ionic solid, the ions are arranged into an alternating set of positives and negatives called a crystal lattice. That's what that thing is called in the metal, crystal lattice. And they are ionically bonded. Only ionically bonded compounds can conduct electricity in water when dissolved. Covalent compounds we saw could not. And the last one, covalently bonded compounds cannot conduct electricity when dissolved because they break apart into molecules and not ions. So ions are required to conduct electricity when dissolved in water. So this is what we need to have learned by the end of this. So hopefully we understand electricity a little bit more than we did before, and what types of things conduct electricity in the solid form, and also what kinds of things conduct electricity in the dissolved form. Okay.